Hello everyone. Today I wanted to show you a little quantum weirdness in C#, where we aim to make variables behave a bit like quantum particles. The first thing we need to do is set the scene. Before 1927, physics had a bit of an identity crisis. Werner Heisenberg noticed that if you try to observe certain properties of a thing, you do not get perfection. You get probabilities, which is a very scientific way of saying it kinda depends. Niels Bohr and Albert Einstein then debated what that all meant, with a sort of polite intensity usually reserved for code reviews on a Friday. Enter the Copenhagen Interpretation. Bohr's camp said that if something can be in several states, then before you look, it's all of them at once. A variable that's quietly A, B, and C, a superposition of all states. Erwin Schrödinger made it famous with a cat that was both alive and not alive until you lifted the lid. We will not be torturing any cats, we'll be writing code. This brings us on to our favourite science communicator, physicist, and philosopher, Richard Feynman, who, in 1982, realised that the state of a particle can be used to encode binary information based on the direction of a spin of a particle. And the point is, if you have a particle that could collapse to these binary patterns before you observe it, then they're all superimposed in a way like this. The result of which is somewhat unreliable, as you can only expect half of an 8-bit value to be something predictable. But what Feynman realized was that by repeating quantum operations on a particle, you can force it to be overwhelmingly probable that a particular pattern will emerge when it collapses. Well, why is that interesting? Well, because in 1999, this guy, Peter Shor, published an algorithm with a series of quantum operations that will cause the particle to collapse to the prime factors of any huge number. With a classical computer, it would take 1 billion years to do, but with a quantum computer, it can be done in 100 seconds. So this brings us on to the year 2000, where this guy, Damian Conway, imagined that you could take different values in a variable and superimpose them. So they're not particles anymore, they're variables. And one of these variables has the value 1, 2, and 3 simultaneously. It's not an array or a list, it's a scalar variable, a single value that happens to be superimposed. 1, 2, or 3. It could be any of them. And similarly, we have another in 2, 3, or 4. So then he asked himself, what if we do mathematical operations on this? What's the result of doing a mathematical operation on something that could be in states 1, 2, or 3 with something that could be 2, 3, or 4? The answer is you get another superimposed variable that could be 2, 4, 5, 6, or 7, because any of the ones of the first variable added to any of the ones of the second variable give you one of these options. So then he realized that there was a piece of the puzzle missing that made it practically useful, and that piece was, when you superimpose, you also need to apply a predicate. You need to apply a selector that chooses what to do when we ask a question. And the predicate that he came up with is the predicate called any. And the idea is that if you apply any to any of these operations, it propagates through the result. And now, if he asks if any of these is true, then it is true. And there's a second predicate as well. Instead, you can say all, and that propagates through as well. Now, if I do an if all of these are true, no they aren't true, that's false, so a predicate gives us a way of collapsing a superposition into a reliable and useful state. Let us borrow that idea in our new quantum-powered C# world. A single variable can carry several candidate values at the same time. Not an array, not a list, one scalar that is many. When you finally ask for a single answer, it collapses into one, until it behaves as if all possibilities are present and accounted for. We will use the QuantumSuperposition Library. It gives us a qubit and an eigenstate, plus the very handy predicates any and all. You'll see that it reads a lot like English. If any of the new values are less than 5, do the thing. Then a comparison of any new against old, then the stricter one, any new against all old. Behind the scenes, the library maps the comparison across all possibilities, then reduces that cloud to a single decision using any or all. You can get the effect of a map reduce without writing the map or the reduce, which is lovely. Let us do a tiny prime detector, because every video deserves a satisfying plink sound when a prime appears. What we did was create a superposition of all possible divisors. We apply the modulo in one go across the entire cloud, then required that all remainders are non-zero. If every branch reports a remainder, the number has no smaller factors and is prime. That was the whole constellation of checks in one tidy if statement. This is where it gets more fun. We introduced time. Positronic variables are special and move backwards through your code, allowing you to print out the answer of a computation before the calculation is done. Here's the simplest example possible. We create our antival, doesn't actually matter when we create it. We then assign 10 to that. It then has 1 added to that value, and then we print out the result of 11 before we've done the calculation. Now this is all lovely and self-consistent, but the naughty part of your brain will be asking, what happens if we try and break it by creating a paradox? And the answer is that superpositions get created, which we went over earlier. You create a two-state wobble in this example. Antivals and vals are both either 1 or 0. What happens in the background is that the system runs the loop until it reaches an output that does not argue with itself. If there are two stable options, it reports a tidy any of both. Here's a helpful way to picture it. Draw your assignment as nodes. Values flow forwards along through expressions. Constraints flow backwards along the same lines. When both flows agree, the line stops wobbling. That's your convergence. If they never agree, you see a superposition. You can sketch these like Feynman diagrams in your code. What you'll note here is there's no explicit loop. You declare the relationship. The engine replays the timeline until the guess settles. Then you print perfectly normal time travel. You can even ask for the outcome you want and let the past fill itself in. Pascal's triangle works nicely as an example of this. You set the target row length, then allow the program to keep stepping until the row matches that length. The result reads like the future patiently explaining to itself the present, which is how I feel when the compiler leaves me a warning. So, quantum superposition gives you many possibilities at once with any and all to make decisions without herding loops. Positronic variables give you many times at once with convergence to settle disagreements between the past and the future. Together, they let you write expressive C# that explores alternatives in parallel, then lets time nudge the result to a stable answer. You can use this for constraint checking and candidate scoring, puzzle solvers, validation across many options, and little neural nodes that fuse several inputs into a tidy set of likely outputs. Use it to make tidy demos where people clap politely and then ask how it works. And then you can say quantum vibes in C# and sip your Earl Grey tea. So thank you to Heisenberg for noticing the universe is coy, Bohr and Einstein for arguing about it with style, Schrödinger for the unfortunate cat, Feynman for the habit of explaining, Peter Shor for showing that amplitudes can bully answers into appearing, and Damian Conway for giving programmers a way to play with superpositions without needing a badge to a national lab. Install the package, try any and all examples, try the prime plinks, a tiny positronic loop, collapse responsibly. If the cat is in a box, give it a treat either way. Hello everyone. Today I wanted to show you a little quantum weirdness in C#, where we aim to make variables behave a bit like quantum